Okay, so for web work 14, problem 12, we have to evaluate the line integral right here, where c is the parameterized path, x equals t cubed, and y equals t squared. So what I thought I might do is just define what the vector field f of xy is. So I mean, obviously it's equal to m I hat plus n in the j hat direction. But what these are really equal to with this definition in the differential equations, m and n are just equal to the coefficients of d of x and d of y respectively. So we can just label these here, m and n, and plug them back into our function here. So where this is equal to y in the I hat direction plus x in the j hat direction. It's really, I guess, to visualize this and see the similarity in what we're doing here versus the standard line integrals where you have r of t and f of t. It might be helpful to see this and realize that and equate this. But with this definition and what we've been given for the parameterized path, it's not necessary to do this to calculate this line integral. So what we have is the parameterized path here, and from 2, this is for the definition. This definition is for t equals 2 to t equals 8. But what we really have are definitions for x and y here, so that they can get plugged right into the function, and you can completely skip this step. As far as evaluating this goes, I know maybe a professor might want to see this, and that you've made this conclusion, but it's not necessary for evaluating the problem. So what we can do is plug these definitions right into this function here to get t squared d of x plus t cubed d of y. And then next we can solve for d of x and d of y using the same exact equations. So if we just take the derivative of both sides of these equations here, we get d of x is equal to 3t squared d of t, and d of y is equal to 2t rather, d of t. And these can be plugged right into our line integral. And that will give us, taking into account that we're going from t equals 2 to t equals 8, that'll give us t squared times d of x, which is 3t squared d of t, plus t cubed times d of y, which is 2t d of t. And this is our line integral that we have to evaluate. So if we simplify this a little bit, we end up with 5t to the 4th, evaluated from 2 to 8. And that, of course, would be t to t. And so what this is equal to is you raise the power, divide by that power. So we'd get t to the 5th divided by 5t to the 5th divided by 5, which is just going to give us t to the 5th. And that's evaluated from 8 to 2. So what we have is 8 to the 5th minus 2 to the 5th, which gives us our ultimate answer, which is 32,736. And that is the final answer, and this would be units of work. So here we have our vector field and the path moving through it. And you can see from the orientation arrows that the path is going to be moving from left to right. And you can also see that the vector field is going to be assisting this motion no matter where you look, as we have it here. And that would make sense because our answer is a very large positive value. So it makes sense that the vector field's always going to be assisting this motion, giving us that large positive value. So our answer of 32,736 units of work actually makes sense in this scenario.